Hello everyone and welcome to today's webinar. Today's webinar is titled Physical Stresses on Caregivers when Repositioning Patients in Bed. My name is Christopher Iversen and I'm from Anybody Technology. Today I will be the host of this webinar and I am here together with my colleague Zhou, who is our Head of Services here at Anybody, and he will join us during the Q&A session in the end. So today we have an external speaker who is Zhou. Victor is an ergonomics researcher at Hillrom, and he's going to give his presentation in a minute or so. But just before we start, I will give you a general introduction, an overview of the Anybody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling in general. So what is the Anybody modeling system? So the Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates internal body loads as joint moments, joint reaction forces, and muscle forces. And here in the bottom of the screen, you can see a screenshot from Anybody. So this can give you an idea of how the system actually looks. And at the moment, Anybody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the fields of sports optimization, orthopedics and rehabilitation, and assistive devices as, for example, an exoskeleton. And the typical workflow in Anybody could look something like this. So you provide the motion data as input and use the body models which you or others have built. And then you provide some kind of environment, which could, for example, be an exoskeleton. You can then use Anybody to combine these things and then run the inverse dynamic simulations, which basically means that you go from motion to calculate the internal body loads and the interaction with the environment in some cases. You can then output the results and use it for post-processing with, for example, some kind of finite element tool, but many users also closes the loop completely by doing some kind of design optimization and run this cycle multiple times. I think this brings me to the end of the introduction, and I will hand over the presenter role to Victor instead.
Okay, great. Yeah, so hello everyone. My name is Zhou. I also go by Victor, so it's easier to say my name. I am currently an ergonomics researcher in Hillrom. Hillrom is a medical device company, mainly producing hospital beds, stretchers, surgical tables, patient handling devices, and many others. We have an ergonomics lab based in Indiana, in United States, and this project is a recent study from our lab. At first, I will talk about some background information. According to the Bureau of Labor Statistics of the United States, caregivers are more vulnerable to musculoskeletal disorders than most other occupations. And repositioning patients in bed is most common patient handling activities that caregivers need to perform in their job. But manual patient handling is associated with the risk of MSDs, mainly due to overexertion, awkward walking posture, and many other risk factors. Although mechanical lifts are generally accepted as the most robust way to reposition a patient, manual repositioning aids are also commonly used because they were cheaper with the initial investment, and they may be more readily available for caregivers to use, and they were perceived to take less time to use. In most previous studies investigated only one type of repositioning aid, tested only one single patient weight, and did not perform a biomechanical analysis or estimate the risk of injury. So in other words, the relative benefits of using different repositioning aids when handling patients of different body weights is still not clear. Therefore, the objective of the current study is to investigate the risk of injury on caregivers when repositioning patients in bed for several combinations of repositioning activity, patient body weight, and repositioning aid. So in this study, we recruited 10 experienced caregivers, mainly nurse or nursing assistants. They have at least 2 years experience working in a position where they regularly reposition patients. Those who had an injury in their upper extremity or torso were excluded. The experimental protocol was approved by a local IRB office. Besides the caregivers, we also recruited 3 simulated patients. They were very different in their body weight. 4 different types of repositioning aids were tested in our current study. So the first type is IR-assisted repositioning device, or AARD. It's like a air mattress, so it needs to be connected to a blower and inflated under the patient. So it creates an air cushion between the patient and the bed surface to make it easier for caregivers to move. The second type is a friction reducing sheet, or FRS. It is made of low friction fabric and designed for use in pairs to reduce the friction between the patient and the bed surface. So basically, nurses use 2 sheets together to reduce the friction and make the movement easier. The third type is turn and position systems. So it is a multi-layered sheet with the bottom low friction layer contacting the bed surface and the top high friction layer contacting the patient. So it's like all 3 layers there with a stickier layer at the top, and the bottom slippery layer contacting the bed surface. Besides these 3 repositioning aids, we also tested a traditional cotton draw sheet. This is like the control condition of our experiment. So in this repositioning aids, the AARD and FRS need to be applied before using and removed after using. The tab could be left under the patient as claimed by the manufacturer of the tab. For equipment, we use the motion analysis system and reflective markers to capture the movement of the caregivers in the activity. And a force platform was used to track the ground reaction force while caregivers performing the task. We also use 2 force gauges to measure the pulling force. You can see the figure there on the right. There were here in the middle. This is the force gauge. So it is attached to a metal bar using a spherical ball joint here to allow free rotation. So these force gauges are selected to minimize the distance between the metal bar and the sheet, the edge of the sheet. So basically, when performing the task, caregivers pull at this metal bar, and their pulling force will be measured by the force gauges. And also, we use 2 reflecting markers at each side to track the direction of the pulling force. And obviously, we use the antibody modeling system to estimate the joint forces and moments of the caregivers. We investigated 3 different patient repositioning activities, including the pull-up in bed, lateral repositioning, and lateral transfer. So the pull-up in bed is also known as patient boosting. It is performed to move the patient up in the bed because patient they slide down toward the foot of the bed. And pull-up in bed usually is performed by 2 persons, 2 caregivers. So we have a researcher on the other side of the patient helped pulling the patient up. For lateral repositioning, it is a task that laterally move the patient from the center to the edge of the bed. It is usually performed before turning the patient so that the patient has room to be turned. This is a 1-person task. For lateral transfer, this is a task that moves the patient from a bed to a stretcher or from a stretcher to a bed. This is also a 2-person task. So we have we had a researcher help pushing the patient from the origin while the caregiver pulled the patient to the destination. So in each test condition, we test 2 times. The order of the conditions are partially randomized. The bed was set by the caregiver to her preferred bed height. The independent variables we investigated include repositioning aids and patient weight. The dependent variables include peak alpha S1 compression, which is the spine compression at the lumbar and the sacral level, and the peak pulling force, which are measured by these force gauges. So the peak alpha S1 compression was compared to 3,400 newtons limit. Basically, 3,400 newton is the injury threshold according to the study from the National Institute for Occupational Safety and Health in the United States. That study is also known as the study of Nash lifting equation. For the peak pulling force, it is compared to the 245 newtons threshold, which is the psychophysically determined threshold derived from the Lipton mutual tables. It is basically it is the maximum acceptable pulling force for 75% female population. So when they were pulling around their waist height level at a frequency of 1 exertion in every 30 minutes. For the antibody modeling, the pulling force, the ground reaction force, and the markers coordinates are the inputs for the model. The model accounted for the anthropometry of each caregiver and reconstructed the kinematics of the trial and test condition. Then in the inverse dynamics analysis, the joint forces and the moments are estimated. These are some typical screenshots of the model. Now I can show some animation of the actual task, some examples. So this is a task that pull the patient up in the bed. So the caregiver, obviously we put the reflective markers on the caregiver, and she stood on the force plate and grab the metal bar and pull the patient up. And her movement was captured by the motion capture system. So all these colorful dots are the reflecting markers. Then in the kinematics reconstruction, basically it mimics the movement of the caregiver. And finally, it's the inverse dynamics analysis, which estimates the joint forces and the loads of the musculoskeletal system. In the statistical analysis, we first performed the repeated measures ANOVA to test the main effect. Then we performed the Tukey test for pairwise comparison. So in all the statistical analysis, a participant was set as a random factor, and the significance level was set as 0.05. Here are some results. So the results indicated that repositioning aids and patient weight significantly affect both dependent variables in all three different activities. First, we look at the pull-up in bed task. There was a consistent pattern in the repositioning aids across all patient weight for both dependent variables. Here, within each, for example, if we look at each patient weight, the peak alpha S1 compression was always highest for draw sheets and tap, followed by friction reducing sheet, and lowest for AARD. So in this figure, we can see the different letters. So different letters indicate the spine compression force that are significantly different from each other within each patient weight. For example, if we look at in the middle, if we look at the 77 kg patient, we see that the AARD is significantly smaller than the other three conditions. There are no significant difference among the other three. In this task, the draw sheets was now tested on the 141 kg patient to reduce the risk of injury, because according to our pilot testing, this condition was too difficult to perform for caregivers. Here in the red dashed line is the 3,400 newtons injury threshold, as I just described. Similarly, when looking at the peak pulling force, so within each patient weight level, peak pulling force was highest for the draw sheet and the tap, followed by the friction reducing sheet, and lowest for the AARD. The dashed line, the red dashed line, is the 245 newtons injury threshold, as mentioned before. So when aligning the injury threshold of spine compression and pulling force, and looking at these two figures side by side, we can see that pulling force are consistently higher relative to the injury threshold than the spine compression. For example, still if we look at the 77 kg patient, so the average the average of the peak alpha S1 compression were all below the 3,400 newtons. However, the peak pulling force exceeded 245 newton in the draw sheets and the tap condition here. So this finding may suggest that pulling force may be a better indicator of the risk of injury than spine compression. So if we look at the different repositioning aids and understanding the relative benefits, only the AARD resulted in force that are below the injury threshold for all tested conditions. Other is or only effective in relatively lighter patient. For lateral repositioning, jaw sheets and type are now tested on the 141 kg patient again to avoid the injury for caregivers. But in general, we can still see a similar pattern on the spine compression and the pulling force. Basically, within each patient weight level, peak L5S1 compression and peak pulling force are highest for jaw sheet and the tap, followed by friction reducing sheet, and lowest for the AARD. Also, after aligning the injury threshold of spine compression and pulling force are consistently higher relative to the injury threshold than spine compression. For example, the average of peak compression, peak spine compression, or below 3,400 newtons for all tested conditions. However, the peak pulling force exceeded the 245 newtons in many conditions. We can see here. Same thing here for lateral transfer. So within each patient weight level, peak L5S1 compression and peak pulling force are highest for the jaw sheet, followed by friction reducing sheet, and lowest for the AARD. The tap sheet was not tested in this task because tap sheet is not designed to be used for lateral transfer according to the manufacturer's claim. Also, the 141 kg patient was now tested again to avoid the possible injury to the caregivers. So we can see that pulling force are still consistently higher relative to the injury threshold than spine compression. These findings, along with the previous findings, collectively suggest that pulling force may be a better indicator for the risk of injury than spine compression. So when looking at different repositioning aids, only AARD resulted in forces that below the injury threshold for all the trials, all the test conditions. Other aids are only effective in light patient or medium weight level patient or lighter patient. Therefore, when choosing what repositioning aid to use, patient weight should be considered, because patient weight basically it determines the normal force of the friction that need to be overcome when moving the patient. Here we have a guideline and a recommendation for selecting repositioning aids based on patient weight. So the green color indicates pulling force less than the pulling force acceptable to 90% of the female population. So the red indicate the force greater than the pulling force acceptable to 75% of female population. And the yellow color is like in between, so it accommodates 75% female population, but not 90%. So the asterisk sign indicate the actual patient weight that are tested in our current study. All other ranges weights are basically estimates. The black line between colors represent the interpolation of patient weight that corresponds to psychophysical threshold of the pulling force. Generally, from this study, we know that draw sheet is unacceptable to perform manually for any size of patients. The friction reducing sheets is only acceptable for lighter patients. Only the AARD or the air-assisted repositioning devices resulted in forces below the injury threshold for all the conditions. However, the AARD needs to be placed under the patient before use and removed after use. Also, it needs to be inflated and disinfected. So mechanical lifts with repositioning sheets probably remain the lowest risk, and the repositioning sheets can be left under the patient. Here I have a comparison between the AARD with mechanical lift. On the left, this is the AARD. So when using this AARD to move a patient, it needs to be placed under the patient first, then connect to a blower and inflated before use. After later, it needs to be deflated, removed from under the patient, and disinfected. So this is, I think this may be a usability concern that can create a barrier for caregivers to use. On the right side of this picture is the repositioning sheet with a mechanical lift. So it is like a big reinforced flat sheet placed under the patient. It has loops on the left and the right side of the sheet. So when the patient needs to be moved, nurses, they connect the loops to the sling bar of the mechanical lift, so they can reposition the patient and do many others. That is another concern. So AARD is not as versatile as mechanical lift. Besides repositioning patients in bed, the mechanical lift can also be used for many other activities. For example, transfer the patient from the bed to a chair to a bed, and mobilizing the patient. All these activities are also known to have risk of injury, and the mechanical lift can help with that, but AARD cannot. There are several limitations in the current study. The first one is, we only look at moving the patient, but the ease of applying and removing the repositioning aids under and from the patient was not investigated. Also, the joint forces on other affected regions are not evaluated. Besides the lumbar spine region, MSDs are also prevalent in shoulders, elbows, wrists, and many other body regions. For the injury threshold of the pulling force, we use 75% female population as a criteria, which may not be conservative enough. Also, only one model of each type of repositioning aids was tested. The effects of other models may vary and should be investigated in future studies. Conclusion, for patient repositioning, pulling force appears to drive the musculoskeletal injuries more than the spine compression. Repositioning aids can reduce physical stresses on caregivers, but most aids are only appropriate for lighter patients, but not for heavier patients. The AARD can be used to safely reposition most patients, but the usability concern may be a barrier for caregivers to use. When using a mechanical using a mechanical lift along with the repositioning sheet is probably still the most robust solution. I want to acknowledge my colleague Neil Wigerman and Nancy McGann for their effort in this project. Obviously, I also want to thank Christopher and Soren for their support from Anybody System. Thanks.
So thank you very much, Victor, and thank you very much for a nice presentation.
Thank you.
So just before we go to the Q&A session, I would like to say a few words regarding our online resources. And if you want to know more about Anybody Technology, you can go and check out our website, anybodytech.com, for events, special dates, and also a full publication list of studies using the Anybody modeling system. You can also check out our website, anyscript.org. This is our community website for people using Anybody. And here you can find multiple online resources as our wiki page, several blog posts, and links to the repository sites. It's also here our forum is located, and you can go there and ask some questions and get help from some fellow Anybody users. Then I would like to point your attention to an upcoming webcast we have on January 12th. It is titled Biomechanical Investigation of a Passive Upper Extremity Exoskeleton for Manual Material Handling, a Computational Study. And you can find the registration for this webcast on our webpage in the events section. And we will also send you the registration on an email. So last but not least, if you have any questions or just want to meet up with us, then please feel free to send us an email at sales@anybodytech.com. And if you are interested in doing a presentation on your Anybody work yourself, then please feel free to send me an email at ki@anybodytech.com.